All right. So, what'd you think about using the discussion thread as a way of kind of reflecting on your pretest and letting you know what you needed to do?
It was nice to see that I wasn't the only one that messed up on certain problems.
Okay. Yeah, there was definitely a trend that got established as to which problems needed the most help. Any other feedback? Liked it? Didn't like it? Do it again? Trash it? What do you think? Was it okay? Doing it that way? I don't know if I'll do it once we get into chapter 3, where we start doing things more normally. But I've been playing around with the idea of trying to set up a discussion thread with like every homework assignment. So then as you do it, you can go on to the discussion and say, I have no idea how to do number 16. And then if a few other people see that, then I'll know, okay, 16 we definitely need to make sure we cover tomorrow before we move on. Or somebody else could get on and go, dude, you just do this. And you could like almost help each other out if you know. And if not, and if several people are saying this is one we have trouble with, I know that that's one to cover the next day. So it's an idea I was playing around with, so that's why I was just wondering how you thought that worked. All right, so first of all, though, some of you really would get more benefit out of the discussion if you made sure you read the directions and commented on the problems that we were actually interested in for today. Many of you commented on problems that were not on the list that we were interested in for today, and so your discussion maybe wasn't as helpful to you because it's not what we were focusing on for today. You'll get a chance to comment on those another day. Okay? So please make sure with those discussions you read the directions first and know exactly what we're supposed to be commenting on. It's going to help all of us be a little more efficient. So today we're mostly just going to focus on quadratic and polynomials that were in the pretest and what I would expect you to know from this chapter. And we're actually going to spend a couple of days with this. So we're going to go through some of the discussion and explanation today on some of those problems that gave a lot of you some trouble. And then next class, which actually won't be until Monday, seems like forever away, but on Monday we're actually going to do kind of a little activity based on the quadratic and polynomial stuff, just to make sure you're really solid with this. Because I cannot express to you enough how important quadratic and polynomial functions are for a lot of other things. Like one of the reasons rationals is in this chapter with it is because a rational is simply made up of a polynomial over a polynomial. So you have to know how to deal with polynomials to have some idea how to deal with rationals. Okay? And there's a lot of other situations where polynomials and quadratics come into play and we have to know how to deal with them. So I want to make sure we really have a solid grasp on those skills. So we're going to take 2 days with those. And then we'll talk about rationals. And then we'll talk about more of the tech and application stuff that was on that second part before we get to the test for this chapter. Okay, so let's get started here. This was one of the first ones that many of you commented on that gave you a little trouble, number 11. Okay, and I think what would help with this problem is if we go back for a second and talk a little bit about quadratics in general. One of the things that happens with quadratics, similar to linears, is that there are different forms that our quadratic function can take. Once we get beyond quadratics, the choices are fewer. pretty much you're either in transformation form or you're in standard form. But quadratics have three forms that they can be in. The first one we call standard form. And that's just our y equals ax squared plus bx plus c form. Okay, that's our standard form of a quadratic. Then we also have vertex form. The vertex form of the quadratic is also the transformation form. So all of the parent functions that we saw last chapter have a transformation form, which means that every single function we can take, every single parent function, we can take that, we can multiply on the outside by some a value. We can take the function itself, and inside of it where x is, we can subtract some h. And on the outside of whatever the function is, we can add a k. We can do that with every single parent function. Okay? When we do that with quadratic, we actually call that the vertex form. Because from this form, we can directly tell what the vertex is. When we're in the standard form, we have to do some work to figure out what the vertex is going to be. Okay, but in this form, we can just tell by whatever the h and k values are that that's going to be the vertex. Okay? Then our third form, excuse me, is the, it depends, sometimes it's called the intercept form, and sometimes it's called the factored form. And that's the one that's going to look like this. Okay, so we've taken this and we've factored it into this. So this is standard form, this is factored form. Once we have the factors, if there are no coefficients on x, then p and q are going to be the x-intercepts. So that's where it gets the intercept form name from. And then we can use that fact to figure out where the vertex would be. But again, it's not going to be a direct thing like the vertex form is. We're going to have to do some work to figure it out. Okay? So those are our three different forms that a quadratic function can take. Now, if we go to this specific problem, based on the information that we're given, which form would fit best? Vertex form, right? We're given the vertex. And then we're given this other point as well, the y-intercept. But because we know what the vertex is, we can put that into this form and start figuring out what this function should look like. So in the first step, we are going to substitute the h and the k. So what should my h value be? X minus what? The -1. Because that's the x coordinate of my vertex. That's what h represents. So if it's minus -1, we're just going to end up with +1. That is getting squared. Don't forget your little square on that. And then what should I be adding for k? A 2. Is that all I need to do? We have to solve for a. How am I going to solve for A?
Plugging zeros in the front.
Yeah, so I have this other point. The other point that's not the vertex gives me another xy combination that I know has to work on my parabola. It has to be a point on the parabola. It has to make this equation true. So if I stick that in for x and y, then all I have left to solve for is A. And so we do that. I'm going to subtract the 2 over first. And if I simplify this part to become the coefficient on A, I'm going to just end up with 1. So A then has to be -2. So now that I have the A piece and I have the H and K piece, the function that represents the entire parabola and therefore leaves x and y as variables to represent all the different possible combinations is going to be y equals the -2 in for A that we just found, parentheses x plus 1 squared plus 2. And because it simply said write an equation, it did not specify this form of the equation that you needed, that's good enough. There's no need to take x plus 1 and square it out and multiply it all by -2 and add the 2 on. There's nothing that says this has to be a standard form. It just said write an equation. Well, the equation that fits best for the information I'm given is vertex, and so I'm just going to write a vertex form equation. Yes, Mike?
How do you change something from standard form to vertex form?
Completing the square. Okay. Do you want to see that right now? Raise your hand if you think you remember completing the square from Algebra 2. Alright, so that is one of the things that's nice to be able to do, is to be able to go from form to form to form. Because there are times where vertex form is more helpful than standard form is. So being able to change it from standard to vertex is good. Or being able to factor my standard into this factored form and know where my x-intercepts is going to be is more beneficial. So there are times where we want to be able to change from form to form. So let me just show you really quick. Okay, we're going to go tough. We'll just throw it all out here. Let's say that I want y equals 2x plus... No, x squared, sorry, 2x squared plus 8x minus 7. Okay, and I want to change that into vertex form. Factored form is pretty easy. If it's factorable, I think we all, I hope, remember how to factor, we can do that. But this is just vertex form. Okay? So we have to do completing the square, which means that I need to make space. Actually, I need to do a couple of things here. Those of you who remember completing the square, do you remember what the key step was? How do you actually complete the square? Say again? How?
Do you get rid of the coefficient on x? Divide everything by 2.
Okay, and then what would you have to do?
And then find the thing that you need to square to get 2a.
Okay, so our little trick of taking half of b and squaring it to get the missing c that's going to complete my square only works if x squared only has 1 as a coefficient. So when it has something other than 1, we have to factor it out of both the x squared and the x term. And then we need to leave space for what that magical c is that's going to complete my square for me. Okay, so there's two things we're going to do here. We're going to factor out 2 from the x squared and from the 8x. And then we're going to leave space for our magical c, and we're going to kick 7 out outside of the parentheses. Okay, we're kicking 7 out because the negative 7 on its own does not complete my square. 2x squared plus 8x minus 7 is not a complete perfect square on its own. So we're kicking that 7 out for the moment, and we're going to complete this square. Now if this had just been this, then all we'd have to do is kick the 7 out and complete the square, and that would stay 8. Okay? But because we have that 2 there, we also have to factor the 2 out of both the x squared and the x term, and now we're going to fill in that empty space. With me so far? It's kind of ringing a bell? All right. So to actually complete the square then, like Elijah said, we're trying to figure out what is it that's actually going to make this a perfect square trinomial. And the trick to doing that is I need to take half of b and square it. So what is half of my b value now?
2.
And if I square it, I get 4. Okay? But if I just add the 4 and walk away, I have now changed the equation. It is not equivalent to the same equation that I started with. Okay? So in order to keep this new equation equivalent to the one I started with, I actually need to add 0. But 0 comes in many forms. Okay? A positive 2 minus 2 is a 0. A plus 9 and a minus 9 is a 0. So we're going to add 0 in a way that is going to give me what I need here, but balance it out here. So that the overall effect is that I just added a 0 and I did not actually change the equation. Okay? But the other thing we have to be careful about is, what did I really just add to this equation? An 8, because this 4 is inside of the parentheses that's being multiplied by that 2. So even though I wrote 4 there, what really got added was an 8. So what I'm going to need to balance that is a negative 8 on the outside. Okay? Now again, if there is no coefficient out here, then whatever I added here would be the opposite out here to balance it. But because this coefficient out in front is multiplying by that 4 as well as the 4x and the x squared, then it's really an 8 that got added here, and I have to subtract it over there to keep it balanced and really just be adding a 0. Okay, so now that I've done that, now I rewrite in the factored form. So we've just created this perfect square trinomial so that I can now rewrite it as a binomial squared. So what's the binomial that if I square it, I get x squared plus 4x plus 4? X plus 2. And then what's left on the outside? And there's your vertex form. Okay? And that process is called completing the square.
Is this one of the pretests, or is this just like a random?
This is just answering Elijah's question.
Oh, okay.
Okay, but it's good to know how to do this. We're going to actually get to some things in chapter 10 that are going to come back to completing the square. Why did I pick that up? So it's good to review if you don't remember for sure. All right, moving on. So I just want to touch on this one quickly. It came up with a few people. And most of you said, I don't know what parent function this is related to. Okay, well you should, because that's what we did last chapter with your Families of Functions booklet. We talked about all the different parent functions. So when you look at this one, and you think about all those we talked about, which one would you guess that was related to? X cubed, right? I mean, if I got something cubed, I'm going to guess the parent probably was X cubed. Okay? And then the next step is, all right, so describe the transformations that must have happened to the parent in order to end up with this one. And that goes back to what I was just talking about. Any function, if we say f of x is our function, can have actually 4 different numbers injected into it to create a new function. And those 4 numbers all have different effects on our graph. And as a whole, they're called the transformations. So, 1 is that I can multiply on the outside by an a. Okay? Outside of the function, I can multiply by an a. On the inside of the function, red, 1, 2, 3, let's do orange for this one. On the inside of the function, I can multiply, come back here, by a b. Also on the inside of the function, I can subtract an h value, and then on the outside of the function, I can add a k. So those are the 4 different numbers that can be injected. 2 of them are for multiplying, 2 of them are for adding and subtracting. And the difference is whether I'm doing it inside of the function or outside. So in this case, if we're saying the parent was the y equals x cubed, right? That's the function that's going on in this parent. So anything that's inside of parentheses before I get to the cube would be considered inside the function. And then anything that happens after the cubing is considered outside the function. You can also think of it in terms of order of operations. If I actually put a value in for x and had to work this out, any steps that have to be done before I get to whatever the parent's about, cubing, square rooting, absolute value, whatever, those are inside the function. And any operations that would happen after I do that major function, cubing, square rooting, absolute value, would be outside the function. Okay? Really quick rundown. A has 2 different effects. If the absolute value of A is greater than 1, we have a vertical stretch. It changes the shape of the graph. If we have something where absolute value of A is between 0 and 1, let me try that again. Then we have a vertical shrink. Okay? So the magnitude of A is going to change the shape of our graph. Make it skinnier or make it wider. If A is negative, then we get a reflection over the x-axis. So that's going to flip it from up to down over the x-axis. Okay? B is similar, but the reverse direction. Okay? So for B, absolute value of B, and I got to make sure I get this right because it's opposite. So if absolute value of B is greater than 1, then it's actually a horizontal shrink. And if it's between 0 and 1, then we get the horizontal stretch. If B is negative, then we're going to reflect, but it's going to be over the y-axis. So A and B have similar types of effects, but in opposite directions. Now, we don't see B that often, and depending on the function, a lot of times B can be pulled out and become an A, and it's easier to think about what it does as an A than as a B. Let me just double check that I got this right, because I always get confused with B. I just want to double check. Whether it's in here or not. Oh, of course it's not going to be in there. Okay, I'll check that a little bit later. If this is wrong, I'll come back and make sure that we fix it later. But I'm pretty sure B is right. I know A is right. So put a little question mark by B, and I'll double check on that one. Okay? The thing with B is that before you can define B and H, you have to factor B out. So if you get something like this, where you're going to take 2x plus 4 and square it, before you can say what H and B are, you have to rewrite this as 2 times x plus 2 squared. And then B is 2 and H is actually negative 2, not negative 4.
That's not positive.
Sorry?
Wait, you said -4, but that's a 2x plus 4.
Right, but your H value is always the opposite of what it
Oh,
looks
yeah,
like,
yeah.
right? Because it's
Okay.
always minus as
yeah.
part of the form.
Okay.
So if this is what you had and you were trying to identify what's my B and what's my H so I know what kind of effects it has, it's a B of 2, it's an H of negative 2. Because you have to factor the 2 out of this whole expression before you can decide.
What's the difference between a vertical stretch and a horizontal stretch?
They're going to look the same, but they're going to happen in different ways. That's why I'm saying a lot of times you can actually take B and make it become an A, and then the effect that it has on the graph is going to be the same, but you just have to know how to make the B the A correctly, okay? And then work with the A. What it looks like on the graph is going to look the same, okay? Because let's face it, when I do a vertical stretch, what happens? It gets skinnier. It looks like a horizontal shrink, right? Okay, and vice versa. All right, and then last but not least, our H and our K. H is going to make things shift horizontally. Okay, and then K is going to make things shift vertically. This thing is so random. Vertical shift. Okay, so H and K just move position. Right, left, up, down. Negative A and B does a reflection. So the shape doesn't change. It's just the orientation that's going to change. And then absolute value of A being bigger than or less than 1 is what's going to actually change the shape on you. Okay? So when we look at this one's pretty straightforward. Which of these do we have? A, B, H, or K? An H and a K, right? So if you know what the parent looks like, our parent for x cubed looks something like this as a quick sketch. Okay? What effect will that H and that K have on this graph?
Horizontal shift 2 to the right.
Okay? And a vertical shift 3 down. So technically my H value is a positive 2 because the negative is part of the form. So positive 2 means I'm going to go right 2. And then the negative 3 out here for K means I'm going to go down 3. So my right 2 and down 3, this is now where my shelf is going to be. And then I just draw the same cubic graph, but in a new position. Okay, so that's how that problem is asking you to work things out. It's giving you something that's technically a polynomial because it's a third degree, but it's giving it to you in transformation form. So you should be able to identify A, B, H, and K and say, okay, well I know the parent normally looks like this, and then these are the transformations that are going to happen. So part B, you're actually going to write shift 2 to the right, shift 3 down, and then make it happen over there. Okay? Does that make a little more sense? Those of you that had trouble with that? Questions? Laddie said 13.
Yeah.
We need a break before we handle 13? Steven's over there going, yeah. Everybody stand up for a sec. Just stretch a little bit. It's early. It's hard to get going. We're going to need full brain power for this one. Just stretch a little bit. Put your arms up. Whoa. Just kind of stretch. Roll your shoulders a little bit. Snug your neck. All right, let's tackle this one.
Yeah, I don't know how to do it.
All right, so when you're asked to graph a polynomial, very few people said they had any issues with graphing quadratics, so I hope that's true, or I hope you can figure it out because you just had little issues. But when we get beyond quadratics and we start talking about polynomials, it gets a bit more complicated. Probably the two, well, I'd say three. The three big pieces that are going to help you are what's listed here. Leading coefficient test, which is going to tell you end behavior. Factoring, if you can, which will tell you where zeros are. And then figuring out the y-intercept, because that's just putting 0 in for x and figuring out what's left. So it's the constant, right? If you can get those three pieces in place, you should be able to come up with a decent sketch of your graph. It may not be absolutely perfect, but it should give you a really good idea. Okay? So, the leading coefficient test is probably one of those that once I explain it, you're going to go, oh yeah. Leading coefficient test is the one that just looks at your leading term, provided that you're in standard form. Okay, so provided that you're in standard form, the term with the highest exponent is first. Okay, that's all we need to look at for the leading coefficient test. And the two things we're going to look at are the degree and the coefficient. Okay, the degree gives us an idea of what the ends are going to be doing. Okay, which parent are the ends going to look like? So if this is a cubic, then the ends are going to look like a cubic. If this was 2, then the ends would look like a parabola. And the beauty is that when it comes to just talking about the ends of the graph, every odd function looks the same, and every even function looks the same. So all odd functions are going to have ends that go opposite directions, and all even functions are going to have ends that go the same direction. Okay? But do they both go up or do they both go down? Is it going right up, left down? Right up, left down? Or the other way? Okay? That's where the leading coefficient comes in. Because if we think back to A, we know that if A is positive, both ends go up on a parabola. Or if A is positive on a cubic, then it's right up and left down. But if A is negative, that's when things flip over the x-axis. So if A is negative, then on anything with an even degree, where both ends should have gone up, now both ends are going to go down. On anything with an odd degree, where it should have been right up, left, down, if the A is negative, that's going to switch. It's going to be left up, right down. Okay? Now, this doesn't tell us what's going to happen in the middle. This just tells us what to expect on the ends. So in this case, what is my degree? 3. That's odd. So I'm expecting opposite directions. What's my coefficient? A positive 1. So should it be right up, left down, or left up, right down?
Right up, down.
Right up, left down. So I know what the ends are supposed to do. That's my first piece of the puzzle. Okay? And to actually describe it, we go back to what we did in the end behavior box on our analysis. We simply say, as x approaches negative infinity, where's f of x going to go? Negative infinity, that's the left side. And as x approaches positive infinity, then where's f of x going to go? Positive infinity, that's the one going up. That's what you write to describe it. You just write that statement that we were using for end behavior in the analysis. Okay? Next step asks you to factor this. Now, I had a few people go, oh, I couldn't remember how to factor a polynomial a higher degree. Seriously, look at what you're actually working with. What is always the first thing you look for when you're factoring?
Factor on the back.
Yeah, the common monomial factor. If every one of your terms has a common factor in it, you should be factoring that out first. Well, guess what? They've all got an x. So if I take that out first, then what's left?
X squared plus 4x plus 4. X plus 2 squared.
So now it's just quadratic. You should be able to factor the quadratic.
X plus 2 squared.
Okay, so the factoring step should not have been the part that tripped you up there, if you really looked at what you were given. And I purposely gave you something that even though it was third degree, it could be factored pretty easily. But then the other part of that was the multiplicity. And I can understand where maybe you don't remember that part. The multiplicity is how many times did each factor get used as a factor. So I have two factors here. I have an x and I have an x plus 2. How many times did the x get used as a factor?
One.
Just once. So it's got a multiplicity of 1. How many times did the x plus 2 get used as a factor?
Twice.
Twice, because if I'm squaring it, then it means I used it twice to multiply. So the multiplicity usually is just related to what's the exponents on the factors. Now, why is that helpful to know multiplicity? Because it tells me what's going to happen at the x-intercepts. The factors are going to tell me where the x-intercepts are. The multiplicity tells me the behavior at each x-intercept. Okay, so if I have x and x plus 2 as factors, where are the actual zeros?
X, 0 and negative.
0 and negative 2. So I know I have a point here, and I know I have a point here. Okay? What I don't know is what's going to happen at those points. That's what the multiplicity tells me. A multiplicity of 1, where the exponent is 1, means the graph is going to act like a linear. What do linears do when they yeah, I'm not sure how to actually ask that, so we'll just go with the answer. Linears at x-intercepts just go straight through, right? It's a line. So if there's an x-intercept, a linear is just going to go straight through it. If I have a multiplicity of 2, then my graph is going to act like a what? A quadratic, a degree 2. And what does the parent quadratic usually do at the x-intercept? Bounces off it, because that's where the vertex is. So, wherever our multiplicity of 2 x-intercept is, that's what the graph is going to do. It's just going to touch it and bounce back. If I had a multiplicity of 3, now what's my graph going to behave like? A cubic, right? 3, cubic. What does a cubic behave like at the x-intercept? It's what? It crosses, but is it just boom, straight through? Yeah, you get that shelf, right? You get that little woo, flattening out, and then it takes off again. So if you get a cubic, we get the shelf. And then from there on up, evens act like quadratics and odds act like cubics. Okay, so that means that I know I'm going to go straight through this one. I know I'm going to touch this one. I know that this end has to be going down this way. I know that this end has to be going up this way. I'm already starting to get a pretty good idea what this looks like. Okay, now in this case, is the y-intercept going to add anything to my information? No, because where's y-intercept? It's at 0, 0 also. But sometimes it does. If I don't already have an x-intercept at 0, the y-intercept is going to be somewhere else. And so that's one more piece of the puzzle to help me put this all together. Now, if at this point you want to find a couple of other points just to make sure, you can. Like, for example, I'd kind of like to know just how big a bump is going to be in between those two. So I could put in -1 for x, figure it out. It's easiest if I put -1 into the factored form. So it means I'm going to have 1 squared, which is 1, times -1, which is -1, so beauty. Oh, wait. No. Did I say that right?
Yeah, but
-1, 1 squared, 1. Okay.
so how does that work?
Okay. Yeah. Okay, so how does that work? Because what happens at -2? I bounce. So if I'm coming up from here, I hit -2 and bounce, then I can come back and get this point and then do my straight through there, and boom, I got a graph. And that's all I'm looking for. It does not have to be a point-by-point, absolutely perfect graph. I just want a general idea with x-intercepts, y-intercepts, and correct end behavior. Yes?
For A, so you said that if there's a positive coefficient, then it's right up, left.
For a cubic,
Yeah.
right up, left down. Yep. So right's up, left's down because my coefficient is technically a +1. Yep. Any other questions on this one? Make sense? All right. I want to talk about this one really quick. This one also came up, even though it wasn't in the list. A lot of you said 27. It kind of goes along with this because we're trying to solve a cubic. Maybe we do need to do this one because for what you're going to do next class, maybe we need to go through this one quick. So let's do it quick. The other things that were mentioned, let me just show you really quick. Complex numbers. The biggest one was 20. The goal with number 20 is that you have to get it back into a complex number form, a standard form for complex numbers, which means you can't have a complex in the denominator. So the whole key to this is, what do I do to get rid of the complex number that's in the denominator? Plus 3i, yeah. They're called the conjugates, right? 1 minus 3i, 1 plus 3i. They're not opposites, because if they were opposites, I'd go from a 1 minus 3i to a negative 1 plus 3i, right? So these are conjugates of each other. And what happens is, if I multiply by a conjugate, plus 3i, it's like multiplying difference of squares, right? Something plus something, something minus something. When I multiply it out, the middle terms cancel out, and all I have left is the first and last squared. So if that happens here, my first squared is going to be 1. My last squared is going to be a 9i squared. But what do we do with I squared? Yeah, it becomes negative 1. So if I replace I squared with negative 1, it means I end up with 1 plus 9, and 10 becomes my denominator. Poof. Complex is gone. And so now if I do this on the top and the bottom, because if I multiply by 1, it stays equivalent, then whatever I get on top, I simplify that, I put it over 10, I simplify that as much as I can. That's my new standard form complex number that I get. Okay, but that's why we multiply by the conjugate here, is to get rid of that complex number in the denominator and make it just a rational number.
If it's I cubed, what would it be? Would it be negative square root of negative 1?
Yes. Okay? And so that's what happens with all of these. When you're dealing with the I, just think of it like x. What would you do if that was x? So you'd add and subtract like terms, you'd FOIL, take this and square it like you would with anything else. It's just that when you do all that, if you end up with an I squared, you just have to replace it with negative 1 and then simplify. Okay, and you can see that in the book. Dividing, take a look at those two in the book. If you have trouble with that, we can talk a little bit about it next class before we start our activity, but I think if you look at it in the book, it will refresh your memory. Okay? All right, really quick, back to this one. Rational zero test. P's over Q's. Where do I get P values from? Close. The constant. The P's come from the constant at the end. The Q's come from the leading coefficient. Right? So I always get kind of biblical on this one. The first will be last and the last will be first. Alright? It's the last one that goes on top and the first one that goes on the bottom. And you want all of the factors of it. So your P over Q rational zeros list here comes from every combination of the factors of the constant over the factors of the leading coefficient. In this case, that's easy because my leading coefficient is just 1. So what are the factors of negative 5?
Negative 5.
Say again.
Negative 1, negative 5.
So remember, every factor you come up with, they're all going to be plus or minus. Because regardless of whether it was a negative 5 or a positive 5, even if it was positive 5, I could have done negative 1 times negative 5. And we want all the positives and negatives when we're thinking about this in this context. Okay? And since all of those are going to be over plus or minus 1, that's just it. Plus or minus 1, plus or minus 5. Okay, Descartes' rule. Anybody here seen this before? I don't know if this is an Alice 2 thing or not. A couple of you? Okay. Descartes' rule is kind of funky, but it's kind of fun. And it just gives you one more piece of the puzzle so you know what you're looking for. Okay? So we've said now that there's 4 possible rational zeros. Okay? If there's going to be a rational zero, it has to be one of those 4. Positive 1, negative 1, positive 5, negative 5. This gets us a little bit more specific and says, okay, but here's how many real zeros you should expect. Okay, so maybe we get into some square roots, those kinds of things. Here's how many reals to expect. So you take the f of x, right, the original function, and you look at number of sign changes.
I remember this.
Sounding familiar?
A
Okay,
little bit.
so you just, from here to here, did this sign change? Yes, there's one. Did this sign change?
Yes.
There's two. This one.
Yes.
There's three. Okay, so I have 3 sign changes. So there's possibly 3 different real zeros to my function. But it's also possible that not all of my zeros are real. I may have some complex ones. Well, if I have one complex zero, I have to have 2, because complex zeros always happen as conjugates. There's those conjugates again. Okay? So, if I have some complex zeros in there, that means 2 of them could possibly be complex, which would leave me with a possibility of how many reals then? Just 1. So it might be 3, or it might just be 1 positive real zero. Okay? So whenever you take your number of sign changes, you take that number and then you just keep decreasing by 2 until you can't anymore, until you get to like 0 or 1, because then it wouldn't make sense to keep decreasing from there. And that's the different possibilities. So it might be 3, or it might just be 1, because some of them might be complex. Okay? For the negative real zeros, we do the same thing, but we have to take f of negative x. So what we're technically doing is putting negative x in place of x in our function, simplifying, and then looking at sign changes there. The shortcut to that is every exponent that's odd will actually change their sign. Every exponent that's even, because I'm going to take the even exponent of a negative, means nothing's going to change. So, when I rewrite this, that's an odd exponent, so that's going to become negative. That's an even, so it's going to stay as is. That's an odd, because it's just 1, so that's going to change to a negative 7x. There we go. And then that's just a constant, so there's no way to change it, because there's no x to put in. So now, how many sign changes?
None.
None. Oops. Now, why is that helpful? Because I had 4 possibilities up here, and rationals are reals, right? Positive 1, negative 1, positive 5, negative 5. If I was doing this by hand, there's no way I would start with the negative 1 or the negative 5, because I just proved to myself there are no negative reals. So I've narrowed down the list of where to start. Okay? Now, the reason this problem was on your calculator section is because at this point, to get to the factoring, we have to do all that synthetic division, right? Well, if I don't have a calculator, I just have to start trial and error. If I have a calculator, I can type in my function, look at my graph, and see if there are any x-intercepts. Because every x-intercept indicates a 0. So when I look at the graph of this, I think it was 5, wasn't it? Anybody got the answer in front of them?
X minus 1 and then x squared minus 2 is 5.
X minus 1. Okay, so 1 was one of my x-intercepts. That means 1 has to be one of my zeros, which means 1 is a fantastic place to start with my scientific, synthetic division. Okay? Because it's on my list, it's one of the positives, and I can see it as an x-intercept on my graph. Okay? Now, the line I'm going to use here, remember, is the coefficients from all of the terms in my function, and I have to make sure that I include all of the different exponent terms. So if you're missing one, you got to put a 0 in. Okay? I'm not missing any here, so I'm going to go 1, -3, 7, -5, and do synthetic division. Bring the 1 down. Multiply, add. Multiply, add. Multiply, add. Bingo. That 0 at the end means I have no remainder, and this really did come out evenly. This really did give me a factor. And what I'm left with now is a 1x squared minus 2x plus 5. Can that be factored? No. So how am I going to come up with any other zeros from that if it can't be factored? Say again, Kate? The quadratic formula. Yep. So if you can't factor this, then you got to use quadratic formula to see what kind of answers you get. And that's where our complex answers came from. If you look at the answer on the key, your other two answers are complex answers because when you work out quadratic formula, that's what happened. Okay? So when it comes then to finding all of the solutions, if you had set this equal to 0, we would say 1 is a solution, right? That was that one. And then whatever two solutions we came up with from our quadratic formula would be the other ones. What did you say it was again, Hunter? Did you have that there?
I just have x squared minus, find all solutions. I don't know if that's right. I got x equals 1 and then 1 plus or minus 2i.
Yeah,
No, I
that sounds
think
right.
that was on the answer.
So when you simplify out the quadratic formula with the imaginary answers that you get, this is the answer you get. Those are the other two solutions. And because it asked for all solutions, we need to include the complex. If it had just asked for real solutions, then we would only say the 1. Because the 1 plus or minus 2i would not be real. Okay? But these are the two steps that I'm interested in. Being able to use the rational zero test, which is that p over q, factors from our constant over factors of our leading coefficient, and then using Descartes' rule to check number of signs and tell me how many positive reals and how many negative reals you would expect from those change of signs. And all of that just helps you narrow down the list as to what we should try. If you have a calculator, that makes this step easier. But if you don't, then it's like, okay, well at least I'm only down to 2 options now instead of 4, because I've just established I can't have any negatives in the reals. So I'll try a positive 1, see if it works. I'll try a positive 5, see if it works. And I'm just narrowing down that list. Okay? Questions? Yeah? We good? That didn't take as long as I thought. You must just have to brush some dust off your brain cells, yeah? All right, so do we need to go through this slower? I really thought that last one was going to take longer. That's why I kind of rushed through it. Do you want to go through this one a bit slower? Okay. Everyone's okay on this one now? All right, let's go through this one a little bit slower. La, la, la. The magic of the eraser. There we go. Okay, so as I said a minute ago, when you're dealing with complex numbers, there is this standard form that our answers should always end up in. And the standard form is always A plus BI. A is called the real number part, and B is called the imaginary number part. And those two parts together give you a complex number. So if you remember our boxes from the other day, was that here? No, that was L2, wasn't it? But we have the boxes where this is the real, right? And then we've got rationals and irrationals. And then we've got all the boxes here for integers and whole and natural and so on. Okay? We now are extending the box. Oh, that's not actually how I want to draw that. Let me try that again. Is it? Oh, is that how I want to draw it? Oh, geez, hold on. Yeah, I think I want to do this. So there's a bigger box around the real box, and these are the complex numbers. So the real numbers are part of it. The real numbers are if b is 0. Right? Because if b is 0, then all we're left with is just the real number part, and so we've got real numbers. Okay? Then we've got this box over here, which is just the pure imaginary numbers, and that's when a is 0. So all we've got is bi, 4i, 2i, negative 3i. Okay? But when we put the two together, we have this box called the complex numbers. So it includes just reals, it includes just imaginaries, but if I put them together, then I've got complex. Okay, so it's a bigger system than just our reals. But the nice thing is that when you go to do operations with them, the operations work as your instincts tell you they do. So what your gut probably is telling you should do with these is what you should do with these. I is not a variable. I represents a value. Okay, it's kind of like having the symbol pi represent 3.14, or having the symbol e represent about 2.78, something like that. Okay, I represents a value. And that value is the square root of -1. So it is not a variable, but when it comes to doing operations, you can think of it like a variable. So that means 7i and I there are like terms. They can be combined. This 5 and the 3 there, the real parts, those are like terms. They can be combined. Since I'm just adding those two together, I'm just going to add reals with reals and imaginaries with imaginaries, and boom, I got a new answer. Same thing with subtracting. You just have to make sure you distribute the negative before you do the combining. With multiplying, we're going to FOIL. So firsts would give me 15, outsides would give me a -20i, insides would give me a -6i, and lasts are going to give me a +8i squared. But I can't leave an I squared in my answer because that doesn't fit standard form. So that's where we have to recognize that I squared if I square both sides of that, then that means I squared is really just equal to -1. So I'm going to replace the I squared here with a -1, which means my +8 is now going to become a -8. And so now the 15 and the -8 becomes 7, and the -20i with the -6i becomes -26i. Now my answer fits standard form. Okay, so where it gets a little tricky is when we talk about dividing complex numbers. Because if I want my answer to end up in standard form, I have to not have a complex number in the denominator. Okay, so as I mentioned a minute ago, the way to get rid of that complex number is to multiply by its conjugate. So if I start with 1 minus 3i, I'm going to multiply by 1 plus 3i. That's going to set up the type of situation that when I multiply this out, when I FOIL it, the 1 times 1 is going to be 1. The 1 times the positive 3i gives me positive 3i. But then the negative 3i times 1 gives me negative 3i. And then my lasts are going to be a negative 9i. So my 3i terms here are going to cancel out because outsides are positive and insides are negative. The I, whoops, sorry, forgot my square there. The I squared is going to get replaced with a negative 1. So my negative 9 is going to become positive 9. And so what I'm now left with is just a real number. 1 plus 9 is 10. So that's the magic it takes to get rid of that complex number in the denominator. I have to multiply it by its conjugate. Okay? But if I multiply the denominator by something, then I have to multiply numerator by same thing. Because I don't want the value of this to change, I want the form of it to change. So in order to keep the same value, I need to multiply by what is essentially 1, which means same thing on top and bottom. So if I multiply the top by 1 plus 3i, now when I FOIL, I'm actually going to end up with some stuff that's probably not going to all cancel out. But that's okay because it's in the numerator. So 2 times 1 is 2. 2 times the 3i, 6i. Negative I times 1 will be negative I. And negative I times 3i is going to be a negative 3i squared. Okay, well again, I squared can be replaced with negative 1, so negative 3 is going to become plus 3. And so now 2 plus 3 will give me the 5. And 6i minus I will give me the 5i. Am I done? Can I leave my answer like that? Factor out the 5 because what I want is this. I want to end up with an answer that's in this a plus bi form. I'm getting closer, but I'm not there yet. So now you can think of it as factoring out 5. You can think of it as splitting this up, putting 5 over 10 and then the 5i over 10 separately, and then simplifying. So the 5 over 10 gives me the 1/2, and the 5 over 10 here also gives me 1/2 to put as a coefficient on I. So 1/2 becomes my A value, and 1/2 becomes my B value, and 1/2 plus 1/2 I becomes my complex number in standard form. Yes?
So you can't leave it as 1 plus I over 2, you gotta split it up.
I would prefer you split it up because we want it to be in standard form, and standard form is A plus BI. So it should look like that form. Yep. Okay? And then with 21, where we're taking 3 minus 2i squared, again, you can either use the tricks you know about taking a binomial squared, first term squared plus 2ab plus second term squared, or if that kind of escapes you for a minute, then just write out 3 minus 2i, parentheses, 3 minus 2i, another parentheses, FOIL. Okay? The operation should work like your gut tells you to make it work. The trick is making sure that anytime you get an I squared, you replace it with negative 1 and then simplify it down to standard form. speaking of standard form, there was one thing I forgot to mention back on our first slide. Remember when I showed you this? And I said we had these three forms, standard form, vertex form, and intercept form? This is the definition I'm using. The book's is different. If you start looking this up in the book calls this standard form. And I don't know why, especially because the guy who wrote this textbook wrote all of our other textbooks as well, except for the orange geo book that you use in honors geo. All the other textbooks that we use in our math series up to this point is written by the same guy. And in any other book, he calls them by these names. But for whatever reason, he gets to this book and decides to start calling vertex form standard form. I love textbook authors. We are not going by his definition. We are going by our definition. We're going by the definition you've been learning for 3 years. Okay? Standard form is going to be considered the y equals ax squared plus bx plus c. Vertex form is going to be considered the a times x minus h squared plus k. Okay? So if there's questions on quizzes or tests, this is what we're going by. Okay? All right, what do we got left? Come here. Want to do some dividing? This is another one of those that you kind of have to let your gut take over. Because the way that you divide polynomials is very much like how you would divide numbers in terms of steps. Now, in terms of what you're actually working with, that's different. But the steps you take are very much the same. So when you get stuck on a step, think about, what if these were just numbers? What would I do next? Probably what you would need to do with polynomials. One of the questions that came up in the comments, which I thought was a good question, comparing 15 and 16, right? Those are our two division problems. And there was some comment about, can I do synthetic with this? Does it have to be long? Can I even do long? But there's this question of, I know there's this thing called synthetic division. Can I do that with this? What's the answer?
Yeah.
Can we do synthetic division with this kind of problem?
We split that up to x plus 1. Neat thing. You go like either one first, right?
Okay, so that's actually an interesting point. As is, if we're just going to flat out divide by x squared minus 1, the answer is no. Okay? Because in order to use synthetic division, you have to divide by something that's in x minus c form, which means it has to be linear. Okay? X squared minus 1 is not linear. So normally, this kind of situation would dictate long division. So let's do that first, and then I'm going to come back to what Rohit said in just a second. Okay? So if we do this by long division, which one's going to go inside of our bracket?
X cubed minus 4x squared plus 10x minus 6.
Am I missing any terms? Like, does it go 3, 2, 1, 0, or?
Yeah.
Yeah. If I'm missing terms, remember we want to put a placeholder in there with a 0. But this one's got cubed, and then squared, and then linear, and then constant. So we've got all of our terms in place. Which means x squared minus 1 is going to go on the outside. That's what we're dividing by. Okay? So, just like with numbers, our first step is to decide what can I multiply by that is going to give me my next line. Now with numbers, our goal is to multiply by the biggest number possible that gets us as close to the number without going over. But with polynomials, it's a little different because I have to multiply by something that gets me exactly that first term. So in this very first step, you're really just concerned about what the first terms are. What do I multiply this x squared by that gets me exactly that x cubed? X. And I highly, highly, highly recommend that you keep like terms lined up. So I'm going to write the x all the way over there on top of the other x term. Okay? And then I actually multiply. So x times x squared, x cubed, and x times negative 1 becomes negative x, which I'm going to line up again with the other x terms. Now what do I do with that? Think about numbers. Once I've done the multiplying, what do I do with that? We subtract it. So that's what I'm going to do here. I am going to subtract the entire thing, which is usually what gets us in trouble. We usually do okay here because the whole point of this is, oh, that goes away. Right? X cubed minus x cubed is supposed to be nothing, and that's what is supposed to happen. So we're usually okay on that first step. Negatives out there where we can see it, everything goes away. Beauty. Where we usually get in trouble is on the next steps. Because we start doing these other terms and we forget that it's minus out here. And we get to something like 7x minus x and we go, oh, 6x. No, it was minus the negative x. So what I highly recommend to you again is that before you actually go combining like terms, add all the opposites. Then when your brain wants to add, you can let it. Because your brain's going to want to add. So now, my x cubed still cancel. Since there's nothing here to combine with, I'm just going to bring down the negative 4. Hello? Hello? We going to write? Maybe? Kind of? Sort of? Oh, come on. What happened? You're doing so well. Seriously? Yeah, obviously there's a crash report. Don't send, just reopen. Yes, reopen.
It's being moved. It doesn't want to be working right now.
Oh.
It wants to go back to sleep.
I got a notebook up here. Let's see if it actually opens up or not. Smartboard, found crash recovery data that might allow you to retrieve yeah, recovery. Okay, really quick. Let's try to finish this up. Maybe. Come on. Where were we, right? Oh, it's gone. There. Okay. Really quick. Minus 1, we did x. We said x cubed minus x. We're subtracting the whole thing. We added opposites, and we got negative 4x squared plus 8x minus 6. Now what do I have to multiply by to get this term to make me exactly that term?
Negative 4.
Negative 4. So we do the same thing. Negative 4x squared plus 4. Subtract the whole thing, which means I'm going to add opposites. So I end up with an 8x minus 10. Now, how do I know this is a remainder, that I'm done? Okay, couple of ways. One, there's no more terms here to work with, which is why lining up terms can be really helpful, because you can see I'm at the end. The other thing is the degree of this is less than the degree of this, which makes this now my remainder. What do we do with the remainder?
So you can include over the
X squared, that's one.
So just like we do with numbers, we're gonna make a fraction out of it. We're gonna take the remainder over the divisor, and it's gonna be the last piece of our puzzle here. And that's our answer.
Yay.
Okay? Now, just a really quick look. I'm not gonna do this one. Can I do synthetic with this one?
Yes.
Maybe.
Yes, because it's in that x minus c form. But what's c?
-3.
So what goes out here in the box is a -3 when I have x plus 3 as the divisor. Okay? And then it's going to be 1, 4, -5, -2, and that's what I use for synthetic. Whatever I end up with out here is my remainder. And I do the same thing. I put remainder over divisor to get the last piece of my answer. The rest of this are the coefficients on the polynomial that is 1 degree less than what I started with, because I'm only dividing by a linear. So I can only come down 1 degree. So if I'm starting with a 3rd degree, the coefficients on this are going to be quadratic. Something x squared, something x constant, and then that over x plus 3 as the remainder part. Okay? All right. Our cracks didn't hurt us. Go ahead and pack up.